Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's live presentation from the Enercon Surface Treating Laboratory, where we will use KRŵSS diagnostic equipment to reveal how Enercon surface treating technology modifies surfaces for adhesion and wettability. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the presentation. We'll reserve time at the end to answer as many questions as we can. Please note this webinar is being recorded, and you'll be able to access both the recording and presentation slides once they are available online, usually within 24 hours. Today, we're fortunate to have two presenters who are experts in the field of surface treatment, surface energy, and adhesion dynamics. Let's go live to the Enercon laboratory and meet KRÜSS's Greg Mead and Enercon's Wilson Lee.
Thank you, Mark. Appreciate it very much. Hello, everybody. My name is Greg Mead. I am the technical sales specialist with KRÜSS, responsible for sales of our instruments in the northeastern United States. I live in the Garden State of New Jersey, responsible for New Jersey, Pennsylvania, and the balance of the Northeast. My educational background is a BS in chemistry, and I have been involved in analytical instrumentation sales for my entire career, which spans 38 years.
And I am Wilson Lee here with Enercon. I've been with Enercon about 8 years. I'm the Director of Business Development, but I've got about 15, 16 years now of surface modification expertise, whether that's atmospheric plasma, low pressure plasma, CO2, Teflon dispersion, a number of different ways of modifying the surface. And what we try to do with that information is when we have customers or we have partners, I try to use that information to help them understand what's going on with their surface and what we can do to help them create the best products they can. So we're ready to go. I think let's get started.
All right. So we're really excited today. We're going to do some live demonstrations. But first, Wilson, we're going to be looking at the results of treatment produced by a wide range of plasma and flame surface treating technologies. Can you start today's presentation by reviewing the difference between plasma and flame and how they activate surfaces?
Of course. These are the technologies that we have here at Enercon. We concentrate on atmospheric plasmas, and there's two forms of those. On the top line there, you can see our air plasmas. On the bottom, you can see the gas plasmas. So when you talk about air plasmas, we have three different technologies that we use. First is the corona. Now that corona is usually used on a film, something a little bit less than 60 mils, I believe it is. It's a large bank of electrodes with a ground roll, and you're treating films and other things in a wide format, usually a roll-to-roll format. But we also have the forced air. That's the blown arc of the blown ion. We'll be showing a blown ion demonstration in this video today or in this webinar today. But those are our air technologies where you are using either the atmospheric air that is just around us, or we're forcing it through a chamber or a tube to treat something. We also have our gas plasmas. We have our flame, which is either using natural gas or propane. And then we have our variable chemistry plasmas. That might be using things other than what's normally in compressed air. So nitrogen, maybe a little bit of hydrogen, noble gases like argon or helium. And all of those things can work together to get different surface chemistries and get different solutions onto the surface. What we always get asked this question: what does plasma actually do to the surface? So it's really doing three things. The first thing it does is clean the surface. Now, mostly this is the organics that are on the surface. Inorganics are a little bit more difficult to clean. Some of them we can clean off, some of them we can't. Some of them need to be pre-treated before we actually do that. But it does do a good job cleaning organics off the surface. It usually takes those hydrocarbons and forms CO2 and water vapor, which just go off into the air, so you don't even see or can even see or smell those things as they're coming off the surface. The second thing it does is micro etch the surface. Now, again, this is a micro etch, so it's on the nanometer scale. You can't see it with your naked eye, but it is increasing the usable surface area with which to bond. So when you sand something or you ablate something, all you're really doing is increasing the amount of area to which the adhesive or the ink can bond to. And the more usable surface area you have, the better your overall bond is going to be. The most important thing that plasma does is functionalize the surface. This is sometimes called activation. What you're really doing is adding molecular groups to the outermost molecular layer of the structure, and this is increasing the energy on that surface. Generally, it's a polar energy. We'll discuss more about that later. But when you activate that surface, you're increasing the surface energy or the surface free energy. And in general, the higher you get that, or when you increase the surface energy, you're increasing your ability to bond to that surface. That's not always the case. There are a few materials that don't work that way, but most of the time, if you're increasing that energy level, you're increasing your ability to bond. These are our three main technologies, or three of our main technologies. One on the left is the blown arc. Now, this is a material or a treater that cannot be used on conductive surfaces, so this is only for plastics. That one nozzle will treat about 3.5 inches wide. We sell it in a single and a dual, so you can treat about 7 inches wide with one machine. Usually runs 5-10 feet a minute. It's perfect for a printing application or a labeling application, something along those lines, or even a bonding application. The middle, the blown iron 125, is what most people think of when they think of a plasma. It treats about 1/2 inch. It's a very intense plasma. The line speeds for this can be from 25 to 250 feet a minute with a single head, depending on what you're trying to do. It also comes in a single and a dual head, so you can treat about 1 inch wide with that. And lately, in the last couple of years, we've been introducing multi-port designs, which are just multiple versions of the 125. So what you see on the picture there is the blown iron 500, which is actually 6 discharges of the 125. The 125 is about 500 watts. The 500 is 3 kilowatts. We've also recently just introduced the blown iron 250, and hopefully here in the next couple of months, the 750 will join it. And that's just allowing us to treat wider distances with a full powered plasma. Our competition generally takes 1 or 2 nozzles and they spin them around to treat wider areas. This is fine on a film when you're a low speed application, but if you need to treat at full speed, you're going to need something a little more powerful, and that's what the multi-port series gives us. And then finally, we have our flame treater. It's part of our gas plasma that we talked about earlier. We use natural gas and propane for this, and the beauty of flame plasma is you do not have to worry as much about the distance from the surface. With all the other plasmas that we talked about, distance and speed are both critical. You need to match both of those to get the same result over and over and over again. The flame allows you to treat things at further away. So what we call it is a multi-dimensional surface, like a dashboard or something. You're able to treat these things very fast, and you don't have to be as consistent with the distance from the surface to get equal treatment. Now, the problem with all three of these is even though we are treating the surface and we can prove that we can treat the surface, you can't see it with the naked eye. So that's why we have Greg here from KRŵSS to show us how we measure these things.
Thank you, Wilson. Appreciate that. How we measure those things with a portable handheld goniometer. So what I'm holding here is our MSA. It's our mobile surface analyzer. This particular instrument has a camera and a light source. You can see the bluish colored light source on the bottom. We're going to deposit drops of liquid onto a solid substrate, measure the contact angle of those liquids. We can then calculate things like surface free energy of a substrate. After we do that, part of the process here, we're going to test, run some things. We're going to see a change in that surface energy of that particular substrate. Again, a photo of the MSA, you can get an idea. It does have a blue button with a ring around the side. That's how you initiate a test. If you can see from this example, there's a slightly curved surface there. That's a question that does come up sometimes. Yes, we can test on curved surfaces. A little bit about what I spoke about. Again, there are 2 different liquids. There's going to be diiodomethane and water filled in each cartridge and placed inside of the instrument. Those liquids are both fully characterized, meaning we know their surface tension value, and we know the polar and dispersed contribution to that surface tension. It's nothing more than the sum of those 2 values. That becomes important for us to know throughout the process because there are things we can do to manipulate each one of those individual components, and we're going to see today, particularly the polar component is what we can impact with the surface treatment for us. Again, just an example of the liquids deposited side by side, and on the right-hand side of the screen, you'll see the flow. We're going to measure the contact angle. We're going to use a mathematical model, in this case OWRK, to allow us to calculate the surface free energy of the substrate both before testing and after surface treatment, and then report the surface energy of that. This is a little bit of a visual example. So we're talking about surface free energy being a sum of the polar and dispersed or non-polar components there. In this example that we're showing here, so we have a liquid and a solid. Both the liquid and solid have the exact same surface tension in the course of the liquid, surface free energy when referring to the solid itself. So they're both 50 millinewtons per meter. That's the surface tension, surface free energy. We know we want those two to align to get the best adhesion of that liquid onto the solid. What we're looking at on the left-hand side is where we have perfect alignment between the polar and dispersed contributions. We know that's going to get us the best adhesion and the best success, whether it's a printing application or a bonding application. On the right-hand side, again, you'll see same surface energy, same surface tension for the liquid, but now we have a little bit of a discrepancy in the polar and dispersed contributions there. Again, we're going to get a heat, probably not going to be as long-lasting or as strong as the example that we're showing on the left, where we have perfect resolution of both polar and dispersed.
Thank you, Greg, for sharing those insights on adhesion and surface energy. Our audience is attending today to see a live demonstration, so let's get started with taking a surface energy measurement before treatment.
Loving up here just to not impact the surface, but just an example of our substrate that we're going to be testing here. I'll place the MSA directly on there, and just so the camera can see, you'll see kind of the blue button right there. I'm going to press the blue button. We'll see water and diiodomethane deposited on the surface. We'll take a look at the contact angles. You'll see both left and right contact angles being highlighted. Top line that I'm highlighting here for us, so water contact angle, we have the mean, which is the average of the left and right contact angle for us. Our diiodomethane, same thing. There's our mean contact angle for diiodomethane with both the left and right. And then the important value outside of the contact angles, we're reporting the surface energy of that substrate. And right above my cursor, if you can see that. So right now, pre-surface treatment, we're at 43.24. May not be high enough for the customer's process application that's going to take place afterwards. I'll give the sample there to Wilson. Wilson, if you can transition and run that sample for us, my friend.
All right. This is part of our lab setup that we use for the plasma itself. So we use a conveyor for most of these applications. We have other ways of treating it, but this is usually the most effective so that we control the speed and the distance from the part. We've got our blown arc here. We've got a couple of blown ion 125. We've got the blown ion 500, which we're going to use for this application. And then we have the new 250 sitting here, which will treat about 1 inch. Now, in a situation like this, where we're treating a relatively flat surface, we generally use the 500 because that gives us a nice uniform treatment across that surface. And it makes it easier for the lab tech to use the MSA to get the information that they're trying to gather. So what I'm going to do now, I'll start up the conveyor. We're going to run this really quickly. It won't take a few seconds. Then we're going to take it back over there and see how we did. All right, now we have our sample. Turn everything off. Bring it over. Great.
Thank you, Wilson. Appreciate it. So we have our substrate here. Place the MSA directly on the top. I'm going to press the blue button, and the magic happens. Everybody remembers from the previous example, we have a nice visual, particularly with water, which is on the left-hand side of the screen there. You'll see it's wetting considerably better for us. If you take a look at lines, both 2 here, so this represents water for our second run, you'll see much, much lower contact angle, much better wetting in this case, actually, for both of the liquids. We'll scroll down and take a look at our surface energy value. So we bumped that from 43 to 57, exactly what we'd expect for that particular contribution there. So a successful run. Thanks, Wilson.
Excellent. Now, we ran a variety of materials before the webinar with various technologies at various speeds. Wilson and Greg, can you look at this data and give us some key takeaways?
All right, so this is the nylon we ran, one of 3 materials that we ran. Obviously, with time, we can't run all of these live. So you'll see the initial conditions. I'm going to focus on contact angle. The initial condition for the nylon, we were about 86, 87 degree contact angle. So again, the lower the contact angle, the more wettability that you have, the higher the surface energy and the better the result. So we treated it with the blown arc and went down to a 30-degree contact angle. That's very good. With the blown ion at 25 feet per minute, we were at 24, 25 contact angle. And you can see, as we would expect, as we increase the speed, you were going to lose some of the treatment. So the ion density goes down as you increase the speed. So now we're at 63, 64 contact angle. And then we had the flame, which also did a really good job. There's some settings there on the left we can discuss if you have curiosity about that. But we were able to get that contact angle down to a 26.5. So the contact angle dropped in all of those, so that's a good thing. Greg, would you like to discuss the surface free energy component?
Yeah, so I'll address kind of the polar energy in particular. So the column on the right there, you had made a comment, I think, about the blown ion running at 50 feet per minute, maybe being a little bit too fast. We can see the polar contribution for that test is considerably lower than some of the other tests. So we can tell from the data by being able to take a look at not only the surface free energy value, but particularly the polar component when it comes to the surface treatment that we're doing to better dial in, if you will, the rate at which it's tested and kind of that concentration and all the stuff that you guys are experts in.
Now, this was the ABS, which is the second material that we tested. The initial number, of course, was 97.5 or 95.7, I should say, contact angle, so a very high contact angle. Again, with the blown arc and with both blown ions at different speeds, we were able to drop that significantly down to 27, 22, and 36, as you can see. And then we had a couple of different flame settings, 150 liters per minute, 250 liters per minute. So the 250 liters per minute in this case worked better. It got it down to 53. But you can tell here that plasma, in this case, does a little bit better job treating ABS than the flame does. And this is something we run across quite often when we run samples. That's why we bring samples to the lab, so we could try all the technologies and figure out which is the best for your particular material. You can also see that the surface energy went up in all those cases, as we talked about before. It went from 44 up into the 60s and 70s. Except for the one with the flame where we obviously were not using enough power to treat that material. Lastly, we had some PVC that we treated. Again, the initial contact angle is very high, over 100. And then you can see that with all of the plasmas, the arc and the ion, we were able to drop that down below 50, and in one case below 40. The one thing I want to point out on this is that we see with liters per minute, we barely dropped the contact angle at all. What we did in this situation was actually damage the material. This is a problem sometimes if you have too much power or the speed is not enough. We were running at 50 feet a minute. So we would need to adjust that to make sure that we're not damaging that material and get a better result. Which reminds me of something that happens quite often. We do some of these testing in our labs, or we get some data, and then we hand it off to our customer, and they'll be testing some data on their own at their facility, and they're getting slightly different numbers than we're getting in our lab. So I'm going to let Greg address some of those issues and what you might what you might be able to do about that.
Yeah, thanks, Wilson, and thanks for showing all the data. And we can see that there's a lot more going on than just treating a sample and then running it and throwing the data up there. There's some other information that we need to know to address the question that I get sometimes from my customers also. They're running tests that just don't make sense to them. They've treated the sample, and I'll take your flame lower line there as the example. They're not seeing the change that they would expect to see. To give them confidence that kind of what they're doing with the instrument is correct, there are various standards, if you will, that customers can use to run that have published and known contact angles for both water and diiodomethane, and also published surface-free energy values. I'm thinking substrates like PDMS or Teflon, and I invite them, I'm like, please run that sample, make sure your results for those known substrates matches published literature, and gives them some confidence that the instrument's working as it should, and we maybe need to take a greater look at the process.
All right, before we get to our audience's questions, I do have a question for each of you. So Wilson, there's so many variables of material types, technologies, and line speeds. How does Enercon help customers determine which technology will be best for their application?
Good question. This lab is one of the main parts. Again, your material is going to be slightly different, even if you're getting the same PVC that you think you've been getting for years, maybe using a different vendor. Things change, processes change. We need to take detailed information, and that's what we do here in the lab. So we have a flame treater here. We have multiple flame treaters that we haven't shown today. We have this system that you talk about now. We also have some other things like plasma 3 and plasma 4. So we have lots of ways to test that material to make sure that we're getting the best results for you. And then when we pass that off to you, whether it's a consignment system that we bring to your facility, we can tell you more about your material, what it needs to be treated at, what speeds we're talking about, what distances from the surface. All of these things will help us get a better result. We're not just going to send you a piece of equipment and say, good luck, try to treat this. We hear it a lot. Plasma, we tried plasma before, it didn't work. Well, as we're trying to show here today, there's a lot of variables involved and a lot of things that you can do that will make it not work. But there are also other things that we can do that will help you make that work. So the lab is very important. We never sell a system unless it's an application that we've been doing for years. We test everything. We always test either in our lab or either live before we sell you a system.
Appreciate that, Wilson. And Greg, the part we tested today was a simple flat plastic sample. What's the range of surfaces the MSA device can be used on, and what other solutions would KRŵSS offer?
Yeah, thank you. Appreciate that, Mark. I wanted to piggyback kind of on Wilson's comments with regard to their lab helping their customers understand the process and get confidence that what they're doing is moving in the right direction. I just want to echo that. KRÜSS has the same thing. So we have an applications lab outside of Charlotte, North Carolina, and we invite our customers that have applications that they're not certain about to send samples to us for testing to give them confidence that the solution that we're proposing for them is the correct one and gives them the desired results and information. So we can also do that with our customers. To address your question, Mark, with regard to types of substrates, things like that, what can be done with this instrument? So I mentioned earlier, but we're testing on a flat surface. That's simple. Curved surfaces can also be done with something like the MSA. And what we're showing here is really contact angle measurement. This is a goniometer that we're doing. So contact angle measurement, reporting surface energy off of those values. I want everybody to know, even a simple, small handheld instrument like this has the capability to do liquid surface tension measurements. So if you're in a laboratory and you have a need for maybe something portable to take to different locations to tackle not only contact angle measurement, but surface tension measurements, that really can be done from a small portable system like the MSA. KRÜSS obviously has benchtop instruments also for more demanding applications, for customers that want to introduce automation into their process that maybe can't be done as easily with a small handheld instrument. We're there to support our customers with whatever solution makes the most sense for them.
Fantastic. Great presentation, guys. We are going to get to our audience's questions next. If you do have a more detailed question or would like to reach out to either Greg or Wilson, we'll leave their contact information up here on the screen. Feel free to reach out directly to them. The first question we have is, is the testing compatible for different metal alloys as opposed to plastics?
Yeah, so if you're talking from a KRÜSS standpoint there, usually metals do have a higher surface energy, so they're not as often treated in the fashion that we were treating here today. But there are physical cleaning processes or things that can be done, but the actual test itself and what we showed here today would be independent of the type of substrate.
And to piggyback onto that, as you did before, aluminum is probably the #1 material that we treat. So if I had to pick all of the materials in the world that we treat, aluminum is #1. So we treat metals on a very daily basis, and in the automotive industry, it's very important to be able to treat those.
All right, next question is, how much of a distance change will affect the treatment with a blown ion? I assume they're asking about the distance between the treatment and the surface.
It has a great effect. We use the term in the plasma world ion density, and that's just the number of ions hitting the surface at a time. If I want to increase the number of ions hitting the surface, I need to be a little bit closer, or I need to slow down my process. If I want to decrease, there are certain materials that you can actually overtreat. So if I wanted to decrease that, then I would go a little bit faster or go a little bit further away. we generally start somewhere between 1/4 of an inch and 3/4 of an inch to treat that. Probably 1/2 inch is a nice round place to start. And then if you're running samples, especially if you're running samples not in a lab like ours, what I would recommend is you stay constant on your distance. So pick 1/2 an inch as your distance from the surface and then start varying the speed. If you start trying to vary the speed and the distance at the same time, you're just going to get confused. So pick a distance and then modify the speed a little bit. Of course, here in the lab, we can be exact on the distance and the speed, and that's why we use the lab.
Great. These are great questions. Greg, can the device shown today be used for measuring the contact angle for tubes with a 3 mm diameter?
3 millimeter, I'm assuming that's going to be an OD there. So if we align the tube lengthwise and align the instrument to deposit drops along that length, it is going to be possible, Mark. It will be challenging, and that might be an application that might be better geared for a benchtop system where we have greater control over drop deposition, but possible, yes.
Thanks, Greg. Wilson, can you touch on how long treatment lasts and what are some methods to help preserve the treatment?
All right, there are a lot of factors here. Most treatments start, as we did here, so we started in the part of mid-40s in the surface energy, and obviously it went up immediately after we treated it. That particular part will probably stay in that same 50 to 60 dyne level, surface free energy, I should say, not dyne, is probably going to stay there 2, 3, 4, 5, 6 days. And then we'll start to fall off. And now, two things. It almost never gets all the way back to where it started. So we started in the mid-40s. It's not going to get that low again, but it is going to fall off. So we always recommend that you do whatever your next process step is right after I treat it. So we would go from the treater directly to the printer or the bonder or whatever. And that's going to eliminate variables that you have, but it's going to last a few days. There are a few batch applications where you can treat something and then ship it somewhere and then treat it again, but those are rare. We always recommend that you do your next process step immediately after treatment.
Thanks, Wilson. Greg, the question here is about the droplet volume and how can it affect the final contact angle?
Yeah, good question. So contact angle should be independent from drop volume. Eventually, we're going to get drops that are going to be so large that gravity can play an influence on that. But when we're talking either a benchtop or a handheld goniometer, we do have flexibility with regard to drop volume here. So to flip back to the previous question, we'd be using a much smaller drop deposition than we might for other substrates. For our example here today, we use 1 microliter was our drop size, which is pretty common, but we can make that larger or smaller depending on the application.
All right, looks like we have time for a few more questions. A reminder, you can also reach out directly to our 2 experts here. This would be a question for both of you. Just generally speaking, how extensive is surface treating and devices like KRŵSS used in the automotive industry?
I can go ahead and start.
First?
Yeah, I'll start. The automotive industry, at last count, had something like 130 different applications for surface modification, surface treating. So yes, by far the largest customer that we deal with is the automotive industry. And so we use flame on a lot of different applications. We use the blown ion on a lot of different applications, the 500, the 250. Don't really use the blown arc as much in automotive, mostly because of speed. But yes, all of these technologies are used every day in the automotive industry. And I would defy you to find a car that you've been driving in that has not been modified in some way or by plasma. So I'll let Greg talk about the MSA and how they use that in the automotive industry.
Guess what? If it's big for your industry, it's big for us too. So if you think about all the surfaces involved in the manufacturing of an automobile, I mean, obviously the obvious ones are the external panels. They need to be clean, free of defects before coatings are placed on those. But think about all the touch surfaces on the interior of a car. You've got your touch screens, you've got your dashboard, you've got your seats. Think of convertible pots with hydrophobic coatings that are applied to those. All just an example of surfaces that the automotive industry wants to understand better and make sure that whatever coating, protective, UV protectant that's being placed on there bonds to that surface in the way that it should, and that it's a long-lasting bond for them. So certainly automotive's a big customer for ours also.
We've got a question here on, do you also work on reducing surface energy?
At Enercon, we really do not. There are ways of doing that. Technologies like low pressure chambers can reduce, you can put a nano coating on the surface that will change that surface energy. Mostly what we deal with is increasing surface energy, but if you have questions like that, send me an email, give me a call, I can point you in the right direction. There's some specific technologies that you can use to actually decrease the surface energy.
What symptoms would you see if there was overtreatment?
Like the flame treater that we just saw, I'll start with this one. This one's something we can both answer. You could tell that we didn't drop anything. So most materials, basically all materials actually do treat. It's just really how long does it last. Even a Teflon will treat, but it only lasts for a few seconds. So if we're not seeing any significant results, we know to look at maybe we need to adjust our speed. So again, we'll start at a baseline. We'll start at 50 feet a minute and a certain gap and a certain power level, especially for a flame. If it's a plasma, we'll start at a certain distance and a certain speed. And then we just go. So if you've ever seen one of our lab reports, you'll see that there's multiple treatments. There are multiple line items there for different distances and different speeds. And you can generally tell if you've overtreated something. And then there's some materials, say like polycarbonate, that have a sweet spot that you can still treat it and get the surface energy to go up, but your bonding ability will go down somewhere around 50 to 55 millinewtons per meter. And so, again, there's a lot of different things that are going on in that question. So that's the plasma side of it. I'll let Greg address the KRŵSS side of it.
Yeah, just, real quickly, if we take a look at the baseline like we did before, test the sample pre-treatment, come test it again post-treatment. If we see a decrease in the surface energy for that substrate, that would be an indication to me that something else is going on in the process and we need to look a little bit deeper.
Great. Wilson, Greg, fantastic job today. We appreciate our audience's questions and participation. If you enjoyed the webinar and got something out of it, please let us know. If you have ideas for other topics you would like to see either KRÜSS or Enercon tackle in the future, please share that with us as well. This webinar was recorded. You will receive an email tomorrow with access to both the slides and the video recording. And again, you can reach out to Greg or Wilson if you have any additional follow-up questions. We appreciate your time today, and that will conclude today's webinar.